Good evening, everyone. It's really with great pleasure that I'm able to welcome Philippe Block as our lecturer this evening. Philippe is a professor at the Institute of Technology and Architecture at the ETH in Zurich, where he directs the Block Research Group. This group focuses on computational form finding, equilibrium analysis, optimization, the fabrication of curved surface structures, specializing in unreinforced masonry vaults and thin concrete shells. I'm sure he will show you quite a bit of this. He's also the director of the Swiss National Center of Competence and Research in Digital Fabrication and deputy head of the Institute of Technology and Architecture. He was trained both in architecture and engineering, studying both at the VUB in Belgium and then later at MIT, where he earned his PhD in 2009. And his work very much operates at the interface of both of these fields, bringing together computational form finding and analytical techniques with structural and architectural geometry, digital fabrication, and methods of masonry and concrete construction. His work extends from, we could say, the structural analysis of historic vaulted masonry to the design and engineering of compression structures with complex geometries, advancing the field in unreinforced masonry. His work is not only highly innovative, but also exceptionally beautiful, and includes such acclaimed vault projects as the Armadillo Vault from the most recent 2016 Venice Architectural Biennale. He also worked with Howler and Yoon for the MIT Collier Memorial in Cambridge, if you're familiar with that project. And the work has also been applied to develop construction solutions for developing countries, projects that he's worked on in South Africa and Rwanda, in the latter working with Foster and Partners and others. He's won numerous awards for his research and teaching, including the Hengai Prize and Tsubo Award from the International Association of Shell and Spatial Structures for innovative contributions to the field, the Eduardo Venuto Prize for his research on the structural mechanics and the art of building, and the Golden Owl for excellence in teaching from the ETH in Zurich. He's also collaborated with many architects, international architectural firms, including Herzog and Demeron, SOM, Howler and Yoon, Zaha Hadid, Foster, etc., and has exhibited his work globally at the Design Triennial and the Venice Biennales of 2012 and 16. He's also published extensively, is on the editorial board of the International Journal of Space Structures, and on the academic committee of the Lafarge Wholesome Foundation for Sustainable Construction. He is a highly cited author of numerous publications and co-author and editor of 2 books, including Shell Structures for Architecture, Form Finding, and Optimization. In a very short period of time, Philippe has really become a true leader and innovator in the field. Please join me in welcoming Philippe Block.
Thank you. All right. Thank you, Ayla, for this detailed introduction and for the invitation first and foremost. I'm quite excited to take you all on this between 2 to 3 hour voyage on where I want to share my passion, and that is to look back to the past. Specifically, in architecture, we all continuously look back. We know, of course, our references, we know our history, but in engineering, this is not very common, and a lot has been forgotten as well. So I hope that after my lecture, which indeed will not take 3 hours, you might be convinced as well that we should look back to discover new things. Another way to translate the title, because beyond bending is perhaps a little bit abstract, so bending, the engineering bending and so on. What I will be talking about today is strength through geometry. So we're basically, in many different ways, how you can actually do things different, and I would argue better through geometry, so capacity through geometry rather than material properties or capacity. I will not talk about my work or our work in the assessment of historic structures in masonry, but that is indeed how I started this adventure. I went to MIT to work on high-tech stuff, and I ended up working on historic structures. That is because I met John Ochsendorf, who then later became my advisor and is now my partner in the little excuse of a firm that we have to do cool stuff. These shells, I hope that some of you have had the opportunity to see them live at King's College Chapel at University of Cambridge. Beautiful fan vaults. These are large pieces of stone that are being kept together in equilibrium, still standing happily after more than 500 years. They span more than 50 feet, and they have a structural thickness of only 3 inches to 3.5 to 4 inches at the supports. And again, these are built in times that indeed they're just stone. So they need to have a good geometry to balance these things. There was no reinforcement typically used and so on. But just to translate these numbers, and that is what got me really hooked and curious, is that if you were to cut an eggshell in two, then the thickness of the eggshell proportional, the ratio to the span is proportionally the same as these stone shells. So this I found very remarkable. I found impressive also, particularly when John Ochsendorf taught me that actually these structures were very poorly understood, specifically how safe they were, how long they would still be standing, and how this could even be possible, that these are still standing after so many centuries. One of the reasons for that is that at a certain point in history, more specifically around the 1820s, engineering went in one direction and started to focus more on looking at structural analysis on the sense of stress and material failure. So that is exactly when Navier invented the Elasticity Theory. And that is actually, that split is quite a pity and quite interesting, because there is a very different way to look at structures, and that is when you care about stability, which is needed to explain these many stone pieces and being balanced in 3D, then this is fundamentally not a problem of material failure or stresses. The stresses in these kind of structures are very low. And actually, it's the geometry that matters in these cases. And that is, you see on the bottom right, that is why these Gothic master builders could use these proportional rules to basically see what works, then to scale them up, and so basically to become more and more sophisticated. This, to clarify again, literally centuries, 200 to 300, 400 years sometimes, before the current theory of structures. They also use scale models. They actually, you could see scale models in many ways. Like, so they tested in the naves of cathedrals of what they would want to do afterwards, but also literally scale models. So this just to clarify that, so what I will be talking about is actually very non-typical in engineering, because we have in the last 150 years mainly been focusing on stress-related problems, which are highly, highly appropriate for concrete, steel structures, bending structures, but which will not tell you too much meaningful things about why these masonry structures are standing. So one extremely powerful thing, which or concept principle that I hope most of you know, is the inversion, the duality between something that nicely hangs in tension, and then if you freeze this geometry, then you find the geometry of from a statics point, a perfect arch. So this was already formulated by Hooke in the 1600s. And as hangs the flexible line, so but inverted will stand a rigid arch. Very powerful concept. You also probably know that Gaudi, for example, discovered his forms using these kind of ideas. But it is very tedious to make these hanging models to basically start to design, and that is why mathematicians and engineers started to develop these graphical methods, graphic statics, that allowed to basically have a paper, an analog version of doing the hanging models. So on the right, you see maybe a first hint, but I will not talk about it again too much, is you see the relation between the geometry of the structure, and then the diagram above represents actually the equilibrium of forces. So you can literally start to measure the elements in your diagram to understand the axial forces in the system. So graphic statics, rightfully so, became extremely popular and important because it allowed designers to have the direct relation between the geometry of your structure and the geometry of the forces. So if you compare 86 and 88, you see that 88 is a more shallow structure, 86 is a deeper structure. So intuitively, we know that a deeper structure has, for the same applied loads, smaller forces overall. Or if you didn't know that, then you see this here immediately in the diagram, because you see that overall the magnitude, the lengths of the forces are smaller. So this is obvious for a global change like that, but really to go in the details and to discover explicitly understand the relation between form and forces, this is something that was that engineers, designers knew how to do. So they didn't just design something and then analyzed it, but immediately from the start, this was discovered at the same time. So big designers, well, all of them actually made their masterpieces like this. That's where I come from. Let's now immediately dive in and see what we can do with this. So first, let's see if we can actually build upon these graphical tools to actually extend our design space. So for this, I will start with this extremely boring design case. I want to span in compression. It will be abundantly clear later why I love compressive flow of forces. And we have a circular boundary support. So that's where we need to land, and we want compression only. So I'm sure you're thinking at least of a cupola, or a cupola with a dome with an oculus, like the beautiful rotunda here on campus. Well, in fact, all of these solutions could, for the self-weights, stand in compression only, which means that they could be built in unreinforced masonry, out of stone, out of very weak materials, and so on. So just to clarify, because this is the solution space is really infinite. So you can go from this Swiss cheese to this alien-like thing to this butt shape. They all nicely could stand in pure compression. So how to then even discover all these forms? Because I must admit that not long ago, I also would have gotten stuck with a dome. Maybe I would have thought, let's be a little bit kind of funky about it and punch a few holes. But this is really exciting that all of these solutions are there. That is where I developed for my PhD a technique that extends graphic statics to surface structures, so to compression shells. So always in the middle, you will see the layout of forces, which is a designer's choice. You as designer can actually decide where forces would flow. And then this is the distribution of horizontal thrust. And again, if you measure the forces here, then literally a longer element means more attraction of force. On top, you will always see the equilibrium solution. So just with a simple play and redirection of both topology and force equilibrium, you can discover all these different forms. And this, to me, is extremely important in a world where there are so many tools that give you a sense of sophistication, that just give you a colorful output, that we develop tools that are actually quite painful for the first half hour, but that at least as a designer afterwards, you're teaching yourself and you're understanding the relation between equilibrium and the relation to forces. For example, here, the middle one, in order to get these creases, you see that you need to locally attract quite much more force in order to attract the forces along these ribs that you're creating. So this to me was a total surprise that now we have well over 20,000 users, and many big engineering offices admit that they use RhinoVolt as a starting point. So because what these tools allow is actually to get you a more exciting starting point that actually is already optimized for you. All right, let's now see what we can do. First is, if you follow the flow of forces, I already hinted at why that is. You can build with very few or low quality materials. And the hint was the relation between, if you have a good geometry, so meaning a structure that follows the flow of forces, the stresses in the material are very low. And that is then, of course, why you can use these weak materials. So for this, I will give a few examples using tile vaulting, also called Catalan vaulting, or here in the US, referred to often as Guastavino vaulting. I'm probably preaching to the choir here because there's several beautiful examples on campus of this technique. What's exciting about this technique, for those of you who don't know it, is that you use a lightweight tile and a fast-setting mortar to, once you have the boundary conditions, you can actually build in stable sections without needing support from below. So basically these shells are built without a formwork in space. And this first layer with fast-setting mortar serves then as an integrated permanent formwork to build up the structural depth afterwards. Some of my favorite examples, there's many of them in New York here under the Queensboro Bridge Market. Or I guess most of you have seen those shells in Grand Central Terminal, the Oyster Bar. So just emphasizing here again, what you're looking at is not just decoration, it's actually one of 3 layers of unreinforced masonry tiles that are the self-supporting structure by itself. And then not unimportant as well, that these shells that span up to 40, sometimes 50 feet, are indeed built without formwork. So I think this is quite remarkable. And that was indeed the starting point for John Ochsendorf and Peter Rich. Peter Rich, the architect, John Ochsendorf, structural designer, and Michael Ramage then really pushed it into the project to apply this in an African context. This was the Mapungubwe project in South Africa. This was a very early and humble first experience for me. I did the structural analysis of all the shells, and this was basically quite an eye-opening experience. The reason that John Ochsendorf was called in was that the brief actually demanded to do as much as possible with the local means. And because the Mapungubwe site is extremely remote, it didn't make sense to fly in or bring in any engineered materials. And so naturally, the team came to these local resources. The small twist or change with respect to the traditional Mediterranean technique was, rather than using the fired tiles or bricks, to actually just develop a soil press style that only needed 7 to 8% of cement to stabilize them. Another aspect is that they are not fired, so they are just air dried. You see on the top left, they also don't demand any energy rather than human labor, which is indeed abundantly available in many areas in Africa. So this is Michael Ramage teaching what a week before were carpenters and farmers, the most handy people in the village. And this is our our Kiwi mason, James Bellamy. I always like to tell the anecdote that I learned from James of the image on the top right. The reason that the women are carrying very happily the tiles is because the tiles are actually designed to just take 2 megapascals in compression. If that doesn't mean anything for you for whatever reason, that is 15 times less than the typical humble concrete, so the lowest strength concrete that we use. So it basically means peanuts in compression. But even more important, these bricks that are almost a foot long, if you hold them on one end, then they just snap in bending. So they have absolutely no bending capacity. And that is indeed why the women are carrying the tiles, because the first week was a disaster, with more than half of the tiles arriving on site broken, because the men were not doing it carefully enough. And this I tell as an anecdote just to clarify what I mean by what is really a weak material. So barely any compressive strength, designed for very low compressive strength and no bending capacity whatsoever. So this is actually then the very first shell that was built by the locals. Very traditional tile vaulting, actually. You first build these boundary conditions, of course, on supports. So these are built on formwork. And then you see the white is the fast-setting mortar that allows you to lay this first layer without support, and then the other layers can be added. All the timber, all the bent kind of thin strips that you saw on the inside that is now being built up for the second shell is not supporting, it's actually describing the geometry. Again, it's very important to stick to this compressional geometry. So here a nice summary of the different steps. So you need to first have your boundary conditions to, of course, start to build these stable arches from, and then the timber is there to guide the masons. To me, this is one of my favorite images, the one to the right. Particularly because exactly the same tile, and I held them in my hands. It's really scary to build with them somehow, but it's not scary when you place them where the forces need and want to go. And you see that this weak tile, when placed where compression wants to flow, with one layer additional on top is, of course, already sufficient for the next mason to just progress. A not unimportant detail in this image is the black linear element on the bottom, that is the tension tie. A big difference between a curved beam and an arch that actually uses all this that allows all this efficiency is that the arch thrusts outwards, and if you want to then very carefully control the boundary conditions. If they move outwards, like in a beam would be, or they settle, then you could, this arch would immediately collapse. So with very humble means, local resources, both on a material and on a human side, we managed to build these few things, beautifully integrated in the landscape by Peter Rich. And then the main shells were 18 meters span, so that is, what is that, 62 feet or even more. Again, just unreinforced with these weak materials, so literally dirt cheap. As a first project, going to ETH, together with Professor Hebel, I had an opportunity to do several projects in Ethiopia. And we were asked actually to provide an alternative for this model. This is still the current low-cost housing situation. There is nothing low-cost about this. It's just the non-subsidized part maybe could be affordable for low-cost income. You see that here there's all kinds of things that perhaps are problematic. At the time, there was absolutely no cement in Ethiopia, so that had to be imported. Steel for sure has to be important. They don't have precision timber or wood to make scaffolding, so they use all this eucalyptus wood, which is a poisonous tree in Ethiopia, and so on and so on. So this is absolutely too expensive for most people there. So going back to the Guastavinos, using one of their floor systems, we thought that we actually could maybe provide a better solution. How does it work? The arch is a very good shape for a specific loading case, a thin arch that is, but an extremely bad shape when other loadings need to be taken. And so if you have a big point load, then the force lines would want to go outside of your section, which means that it would collapse if there is no bending capacity. And by locally adding stiffeners, so locally adding structural depth, you can actually provide a path for these compressive forces. And then with the tension tie, what we effectively did is we made an extremely lightweight version of a beam, right? We placed just the arch for the self-weight or the dead load. We added the local stiffeners, and then with the tension ties, we resolved the horizontal forces. So making these prototypes, this was Lara Davis, a research assistant at the time, training the local craftspeople in Addis Ababa how to build these shells. Then we used a stabilized fill, a lightweight pumice fill, to then, at the end of the day, end up with one big package where compressive forces could go basically in all directions. I didn't design the staircase, but I'm happy that they paid attention, that the arches may be a good form. But why I'm showing this project is not because it looks beautiful, actually it looks ridiculously boring, but that was done on purpose. That point was made by an Ethiopian colleague. They wanted to build something boxy, something that looks modern, something that would be associated more with, for example, a concrete kind of element. This is a 2-story house, 5 by 8 meters, so 16 by 25 feet. And the important aspect of this is that as you see it here, but without the window finishing, so the construction of this building was below $40 per square meter. And that is real low cost, and that is because we used local labor and local materials. And so that is the exciting thing. So beyond the first project that I showed actually caught a lot of attention, won some prizes, whatever was important to get this going, but I think this is really where we can make a difference. Then suddenly I got a phone call by Lord Norman Foster, which was one of the most nerve-wracking moments of my life. And he asked us to help him design basically these infrastructural elements for the drone port concept that he proposed to be able to distribute medicine very quickly all over the continent, and they wanted these signature drone ports for this. And so we developed, designed, engineered, and constructed this unit for him at the Venice Biennale. Not that special, but you see perhaps that the shape is a bit more smooth than the one that was used in 2008 in South Africa. And that has to do with our tools evolving, and this geometry has a much more uniform stress distribution, which makes it much more happy to keep these structures in compression throughout their lives. The key research question, though, is can we develop a kit of parts that is very lightweight and simple to be sent, where as a designer you trust that you don't have to send expert masons every single time. And I think that is still one of the big challenges, is that I can give as many lectures as I want about the potential. I think the research that needs to be done, or the commitment, is to develop methods that can, in a safe way, transfer this technology. Anyway, that's what we showed. A big advantage of working with a Starchitect is that this pavilion he convinced the mayor of Venice to keep this for the next 5-10 years on the site, so you can see it next time you go to the Biennale. Invited after all these efforts, again with Dirk Hebel, we were asked to actually do something with this concept. Can you bring this concept to the general public? More people should know about this. And so this was for a project in New York, and okay, we did some explorations on soil and whatever in New York, but that didn't lead to much anywhere. So we tried to translate the concept. In Africa, we have a bundled availability of labor and soil. In New York, you have a lot of waste. So can we, like our buddy Wally, can we start to compress our waste to build something out of it? So this is what we did for this pavilion. No surprise that it's an arch, by the way, right? We found this material that just cuts up these cartons and then compresses them. What's exciting about this material is that it has 1/10 of the strength of a very humble timber and 1/100 of its elasticity modulus, which means that it's extremely flimsy. It's absolutely not meant to be structural. And these kind of things is typically what you have to tell me to get me excited about a project. So let's go. This is a nice little movie of some of the aspects. So it's literally shredding these cartons. Then with a bit of heat, they're compressed. And then you have these very weak boards that you can then use to build something out of. Because it was only there for 4 days, we didn't want to leave anything behind. So the decision was then indeed made to, we only had these white wrapping straps, and there were no glue, no bolts, nothing holding it together, then just, so that is also why we used this masonry logic, because then you had compression nicely keeping these very weak triangles nicely together. The main constraint was that because the site was so expensive that it had to be assemblable by students extremely fast, which was only 2 days. But nonetheless, we had a little bit of fun. So this is orange juice, this is milk, and then so very colorful from one side, and the other side we made black with these wine cartons from the other side. Typically, when I'm not in the US, I say Americans drink wine out of a carton. Anyway, so I will not do that here because otherwise all of you would leave. Sorry, but it's too easy. So that, all right. But so the idea here is really to start from the constraints and to translate the idea that if you have the right geometry that you can use here, this was just 9 millimeters of material, that you can use this weak material to make a cathedral out of waste, perhaps. But more excitingly is not only to use good structural form, meaning compressive flow, to build with very weak materials, but is actually to try, like the Gothics, to do exciting things. I will show a few examples that are done in cut stone. And specifically then, you have another challenge, and that is you are not using standard units, but you need to basically cut up your volume into pieces. That is called stereotomy. And these master masons actually, they had quite a lot going on here, because how these stones are cut up is dependent first and foremost on the structural behavior. So the principal flow of forces wants to be the other way around. The cuts want to be as orthogonal to the force flow as possible. If you don't do that, then you would have some sliding issues and so on. The cuts were also such that it could be constructed, that it could be managed on site. So there was construction was in there. Fabrication was explicitly in there because the way they described the cuts were actually related to how the masons would cut the stones so that there would not be any tolerance issues and so on. And it's also pretty obvious that actually these cuts have quite an important aesthetic aspect and quality as well. So very early little model in 2010 where we try to actually, for these more funky geometries, we can now generate with these new tools how we could do this. So this was exciting in 2010. That's in a time where anything is possible on the computer, that we actually made something physical out of that without glue and without connection. So this was Matthias pushing it. And this is actually a very hard thing to do in engineering. It means that local collapse doesn't propagate in global collapse. Very important. You kill only half of the people and the rest can still get out, right? I'm half joking. That is an important thing when you design this kind of systems, that you understand the relation between local and global collapse. So after that, we had a commission that actually already started during my PhD at MIT. So a very long-term project to do something like that in Austin, Texas. I was inspired by people like Heinz Ziesler, the shell builder in Switzerland in concrete. I was inspired by Fraiotto and his beautiful tensile structures. And so we were trying to get some of these features into this project. It's still on hold. I might even need to start saying that it's permanently on hold. But here we showed some of these early ideas. And as I mentioned, this is actually fundamentally will behave the same as a large structure because it is fundamentally about geometry. But even this is a nice 1 by 1 meter quite extreme shell. So this we tested then, this 860-piece puzzle. All the hands are, by the way, MIT interns for the summer. They thought they were going to do research in my team, but they ended up being model building slaves. No, they also got a few exciting things to do. But this was then showing this model, and because it was going to an exhibition, it had to be glued, and that is why we made this little model particularly for this side. This is again Matthias, being the executioner. So just to put it in context, this is equivalent to Godzilla jumping on one leg on the edge of your shell, not that likely to happen. But if that were to happen, you see that this shell can take quite a lot of abuse, quite a lot of displacements, but then at a certain point, you will have this extremely beautiful collapse. I really was amused by the request by the client to send me the movie without this part, because he was pretty sure that the city of Austin might not have been as excited about the educational aspect of the movie. It was going to the Venice Biennale in 2012, invited by Zahadid Architects in their shell exhibition as one of their inspiration. It was pretty cool to be next to Heinz Isler and Felix Candela there in the corner of that exhibition. But why I show this is because the project that was also on the flyers, the Armadillo Vault that was mentioned in the beginning, was in exactly the same room 4 years later, 20 times bigger. So this is actually quite nice that we actually pulled it off. It's particularly quite nice because our biggest success before that was this most expensive doghouse in the world. This is an unreinforced cut stone doghouse. I can proudly share that we did win Barchitecture 2013, best in show. All right, so let's cut to the chase, I guess, the Armadillo Vault. What you're looking at is 16-meter spans, so I think that translates to almost 60 feet, so 55 feet of span, with only 2 inches of contact thickness in the middle. But that is maybe not that important or spectacular. What is important is that these are 399 cut limestone pieces without any mortar, any glue, and any reinforcement. So this is literally strength through geometry. This is really held together just by its good equilibrium. For those of you who know this building, it's the Arsenale in one of the 2 venues of the Venice Biennale. It's a historically protected building, so that gave us some additional challenges. First, we had to spread the stresses, not to crack the supports. That's why we have these extremely manly supports. And then also, of course, we could not anchor anything. And remember, the reason how you can have this efficiency of an arch, in this case a 3-dimensional arch, a vault, is to resolve the horizontal thrust. It's not just a curved structure. You need to very carefully control the end conditions. And that's where we had this system of tension ties, which we actually decided to expose so that it is very, very clear that that is why this structure is standing. So with the numbers that I said earlier, 16-meter span, 5-centimeter thickness, that meant that almost everywhere, except for very locally at the support, we have 1/3 of the thickness proportionally of an eggshell. That already sounds fairly ridiculous, right? This was actually a big challenge. We had only 5 months to do the design, the engineering, the convincing of the Italians that we are not absolutely bonkers, fabrication and construction, all of that in 5 months. Of course, as academics, totally confident, yeah, but we have this entire digital chain, we know how to do this. I just want to maybe make a point that I don't believe in this kind of stuff. We need to set it up, otherwise you never get there, and you don't allow yourself to discover these kind of new forms. But I start with sketching, so that actually what you input is actually already a good starting point or an interesting one. Then we do some digital sketching. This was done with Rhino Vault. And only then we use our more advanced tools to actually refine the geometry. And the big challenge here is that, just to immediately clarify, this is not just an inverted hanging form. This hanging form had to have so much double curvature everywhere locally so that you could take all these heavy live loads, because this positive double curvature gives you so much effective structural depth that gives your shell that stiffness to stand. A simple hanging model, which we tested, these were our initial steps, they kept collapsing because it was just way too thin. So we had to do a lot of effort to really redistribute the forces such that we achieved this. We went to these 2 inches because that is where we ended up including all the safety factors for extreme live load cases. We wanted at any cost to avoid spalling. So that would have been an issue, and that happens when the truss lines, when the force lines go too extreme. I'm talking about extreme live load cases. It's inside. Well, maybe you can imagine, if you look at the project, the investment was so high that it was important to be able to sell the project afterwards. And so it is actually designed for outdoor conditions, and it is now waiting in boxes to be assembled for the final time in Austin, Texas. We used, sorry for the quality, Matt DeJong at the University of Cambridge used very non-traditional methods to understand the full dynamic response, also extreme settlements of support. So he used discrete element modeling to understand the limits of stability of this structure. But then, unfortunately, the third step, convincing the Italians we were not entirely crazy, took really a lot of time, and that left us with only 1 month to fabricate all the pieces. If we would have done it like this, highly appropriate for beautiful sculptures, but this would have taken us 3 to 4 years to finish the entire geometry. So we went to some more advanced methods like these multi-axis, very big blades, or these wire saws. So this is a hot wire cutter for adults. And what we did basically to get there is to make a few steps that would really speed up fabrication significantly. The most important one was that the blanks would be placed in the CNC and never be moved or rotated or flipped. So this is an extremely important measure, because each time you move or manipulate the piece to mill or process the other side, you need to re-reference everything. You need to, and that is also where you could have tolerance and accuracy kind of problems. So this was step number 1. Step number 2 is that all the side interfaces were cut with these big blades. So this really literally cut through it like butter. Very big optimization step as well. That meant that in front face, all the pieces had to be convex, which means that if you have a shell with negative double curvature, geometrically, mathematically, you cannot tessellate it with a convex element. And that is why the shingling, the offsets on the outside emerged. So that was a direct repercussion on this as a result of this optimization step. Next optimization step was to actually just do the rough cutting and not do the different processes that you do in milling. So we didn't only do the rough cutting, we just jumped always ½ an inch, and we left these pieces of stone. So with a few cuts, we could basically approximate the inside 3D geometry, and then Hector came in to basically hammer all these little stone fins away, so a very big time saver indeed. We calculated that in order for this 399 piece 3D puzzle to come together, we needed to really stay within a 64th of an inch in overall geometry precision, and that is why we developed these profiling tools to shave off the last pieces, because these big blades, highly efficient, but they vibrate a little bit, they behave a little bit after hundreds and hundreds of cuts, so that is why we had these profiling tools to really hit the geometry. All this optimization meant that on the inside we lost our reference, because we have this broken off surface that we don't know exactly where it is. And that is why we included these 6 millimeters, so very, very small registration grooves that assisted the masons to basically position the tiles. This also helped us, of course, structurally, because these small male-female registrations allow us to be certain that even if there is some tolerance issues, that you will not have any local sliding or that that could occur. So that is where the interior surface came from. We also played a little bit with, we tested the overlap of the different cuts so that the stones would, there where you need to split your lines, would cut off at a certain height, so that these higher points created a second layer of fuzziness that started to blend out in the bigger picture. We did a full test assembly in Austin, Texas with our fabricator, our long-term collaborator. People ask, why did you cut this in Austin when you're building in the land of stone in Italy? That has to do 100% with trust. Not trust, just with the T, trust. I had worked already with the Escobedos for more than 8 years. We started during my PhD. They needed to trust that when we designed something with non-typical tools so thin that all their effort and investment would not be in vain, and we had to trust that we had a fabricator that would go all the way and deliver the tolerances that we needed. So after this test assembly, the same crew, the same team, this is David Escobedo, this could be reassembled in just 2.5 weeks in the historic site. So 24 tons, 50,000 pounds of stones, quickly reassembled. I like these images because it is really remarkable, just this one, and you will see another project that we do, is that computational methods, digital fabrication, really allows you to open up the design space quite significantly, but it is really the hand, the experience of the master craftsperson that makes your project a success or not. If we would not have done such an engaged kind of design process on understanding the real constraints of stone setting, of how this is done in practice, and if they would not have shaved off with amazing patience every stone to really align perfectly to be razor blade tolerance, then we would not have gotten there. Anyway, we did get there, so this is the finishing up. An early visitor, maybe some of you recognize Lord Foster himself. He was probably thinking, damn it, I wanted to be on this team. And no. And this is Alejandro Aravena. Quite funny, he actually came by just when we decentered the shell, so we were still in euphoria. And then someone said, but you should see from the top, it's so much cooler. They meant the mezzanine level, and he just started climbing on it, which made me very nervous because we didn't check all the stones yet. There could have been any stone loose or whatnot. But as you know, he's still alive, so this went okay. This movie clarifies the design process, also in the different parts in the world with the different teams. So my team, the Block Research Group, did structural design, first engineering, and the fabrication optimization. We also made this movie to clarify that all the tools that we develop, we share. So through our website, and then particularly also our new computational framework, you can do exactly what we did. Because we find it important to share this knowledge. We take the main dominant force flow to align the stones, then we do the optimization to impose the properties that we have discussed earlier. And actually the cuts are also globally aligned to the force flow to make the piece even more legible or kind of almost educational. And these are the 399 bounding boxes that are then grouped within 56 blanks to cut the local limestone. I always find it funny, local in Texas means 800 kilometers away, 600 miles away, but local limestone, very soft limestone, easy to handle, to cut, and also with very few natural flaws. So here, this is also a summary of what we have already looked at, is that the piece will never have to be flipped, a key thing to control tolerances also. And then with just a few of these cuts, you can then hector hammering away the fins so that they're all somewhat uniform. And then these last passes to really make sure that we hit those accuracy requirements. The test assembly, this was crazy nerve-wracking because we were really running out of time, and we caught a lot of we caught a few mistakes in the geometry description that we changed during cutting. That was one of the reasons that we assembled simultaneously with the fabrication. And then it's quite interesting that it's easier and cheaper to ship from Austin to Venice than from Venice to Venice, because then suddenly you're in a very different world. You lose control. People speak another language. And all your stones and scaffolding needs to go in between the visitors to get on site, which gives you this beautiful footage. but which was quite a challenge. Then you're not done yet. Then we have to maneuver in between all these little alleyways. But then finally we could reassemble, protecting the floor, resetting the scaffolding. David had developed these lightweight jib cranes. This is Frank. To assemble the stones. By the way, this male-female registration cannot be for the last pieces. They have to perfectly slide in. They would otherwise geometrically not fit. So there's somehow like a keystone, but then we had keystone rows. And then after this, they lock the geometry. The stones were all measured from the outside. The corner points were the only references that we have, together with the local reference of the grooves and the local positioning with these wooden shims, which later you will see was a very beautiful low-tech way to know when the shell was standing and not. So here you see these 2.5 weeks. Decentering needs to happen very evenly. Otherwise, it would be equivalent to very uneven, heavy live load. And you saw the shims falling out. That actually meant that the shell was standing by itself. So this was a very easy way to discover when it was safe to take out the formwork. And then we said it's alive because it's called the armadillo, being a Texan native. And also because on the outside it looked a bit like an armadillo's skin, perhaps. So it was there for a bit over 5 months. I particularly like that the optimization necessary for the fabrication pushed us into a geometry that really also clarified and gave an additional layer of legibility, but also strength to the design, that the outside shingling clarified that it was discrete elements being put together, and on the inside, aligned with the force flow, that you got this very different effect and feeling. I have to thank a lot of people and give credit to a lot of people. My team, my office, particularly Matt DeJong and then John Ochsendorf. But then also, of course, the Escobedos. My team was, of course, extremely excited that they spent half a year of their research career doing this rather than writing papers and so on. I focused mainly on arching to activate a masonry structure, but there's many other ways you can balance things. And I just give this as a teaser, so a CCTV tower or something that looks like the Toyo Ito kind of pavilion, is that if you're smart about discretization and so on, that things that don't look like an arch can also take advantage of a masonry model. And this we are now pushing to clarify that you can use these kind of ideas to, for example, build large structures without needing any scaffolding and supports and so on and so on. So when you invite me in 5 years, I hope to surprise you with how the masonry model can be extended well beyond the literal arches and vaults that we see. This was actually also somehow the starting point here. Beautiful project by Mi Jin Yoon. For an unfortunate situation, of course, the memorial for the MIT police officer that was shot after the Boston bombings. This was the initial starting point. This was actually imagined as a concrete structure or a volume structure, and it represents an open hand for the generosity of the officer with a cavity for the emptiness, the missing of that person. But in initial discussions with John Ochsendorf, Mijin then actually changed the direction and sought to see it as indeed an unreinforced masonry structure. You can see this as an extremely shallow vault with 5 buttresses. We went really all out on this project. So Matt did extreme discrete element model, full seismic, full rocking behavior, and so on. We made our typical scale models. Here John is just at 30 degrees, but he will tilt it all the way to 45 degrees, quite convincing for a static equivalent load for a seismic. This is Matt, by the way. Maybe you recognize Mijin and Eric. It's unfortunate that this project happened before the Biennale. That gave us a little bit of street cred, because we had to lose against a linear elastic model that shows you what? Stresses. And I told you already several times that this problem has absolutely nothing to do with stresses. But so it stood unreinforced for 1 day, and now unfortunately there is a little bit of connection pins and epoxy in between there. But because it actually structurally works as a very flat vault with buttresses, we started to go against gravity. And so we control the tolerances in the middle where the shell is the most sensitive, and then we push the tolerances outwards. So here we're talking about 32 pieces only, but of more than 60,000 pounds a piece. And if you haven't seen this yet, I do recommend to go by, because the texture, particularly the design of Meeching and Eric, is really amazing with the polished granite on the inside and the flamed granite on the outside, and all the beautiful symbolism in this project. It is really a beautiful piece. It's particularly beautiful, I find, because it's standing next to the Frank Gehry Center that has so many leaks and so many extension costs that it would be better to tear it down from a cost standpoint. And this beautiful arch will, of course, stand for the next thousands and thousands of years. All right. So let's now see how we can actually go beyond masonry, because how many stone vaults does this world need? How many tile vaults does this world need? At a certain point, this was an important realization for me, is to not use this forgotten technique to do better in an African context, or to propose a more appropriate construction technique, but can we also use this to actually do better in our context? And that's where we developed this unreinforced concrete floor system. So coming back to our arch, I already hinted that this is actually equivalent to a beam, but then you see that in a beam, you need to cover the reinforcements to protect them for corrosion and fire and so on. So you add 3.5, so 1.5 inches of dead weight concrete only to cover these aspects. So what we basically do is we externalize the tension ties so that there we can control them as we need to. And on the inside, we just activate the compression flow. And if you do this on the level of a floor plate, without even talking about optimization, just applying what people used to do all the time, a stiffened shell, you save more than 70% of material, because you basically don't pour unused structural material where you don't need it, right? So, okay, so we seems like a good idea. So we made some little first prototypes. We did the ACI requested entire load test regime. And then after breaking, you see how nicely it stands. Just to make a point here is that I'm also an engineer, but I do realize that my engineering colleagues are the most skeptical animals in the world. So you need to go all out to prove this in every possible way that you can. And here we demonstrate actually that we can take 15 times the required ULS, so maximum loads that is needed to be taken by these floors. All right, I'll come back to those. But something else, strength through geometry. I like shells. This is a Pringle carrying 500 times its self-weight in a bad loading case. We don't see too many big surface structures in concrete, only for unique projects, like the Rolex Center in Lausanne by Sana. And that is because they typically need a unique budget. The unique budget goes to this. You need to build up all this scaffolding. You need to make basically something to pour the concrete on. This means months or sometimes years of custom carpentry or full milling of form. Something else, you need to actually have a foundation to build all of this up, to carry the wet concrete. And then unfortunately, certainly in this project, this was the largest, most precise wooden structure in Switzerland to date. And it turned into this after 28 days. So this to us was a little bit of a pity. Can we address this? Some of you hopefully know Candela. If you go to high par sections, then at least you can reuse all the timber, but you still need the scaffolding, you still need all the labor, you still need all the logistics on site, and you're stuck to, even though he did it amazingly beautifully, but you're stuck to pieces of, in this case, doubly ruled surfaces. Can we be more flexible about our geometries? And that's where we developed this hybrid cable net fabric formwork system. The cable net is the false work, which means it carries the wet concrete, and the fabric is the shuttering, which means that allows you to apply the concrete against it. In 2011, very first prototype, Diedrich on the left, a structural nerd, very appropriate to stand on our little shell. But then, based on this little shell, which was just 2 meters by 2 meters, I somehow convinced the client that we could do it at full scale. So great, we have this project. It will be on top. It will be the unit there on top. So, and it looks like this. So it looks a little bit funky. And we kind of are provoking here a little bit, because maybe those of you who know Swiss architecture, they prefer the straight corners and edges, right? So I am looking forward for my colleagues to go entirely to freak out and kind of to kick me out of the department after this. But what's special about this shell, though, is we are talking about 10 meters by 20 meters by 7.5 meters. So, 35 feet by 60-something feet by 15, no more, 20 feet. A gigantic surface of concrete. This one will be built on a flexible formwork. And then the floor plates, which are full floor plates, 5 by 5 meters, use just a 1 inch, 2 centimeter unreinforced concrete as its structural system. So not talking about the program of the project, this is then literally the structural depth of the project. There's some nice additional research that went into this. If you have a lightweight construction, you have issues with acoustics. But actually what's quite nice, and this is extremely well known in the airplane industry, but never used in architecture, is to use stiffness rather than mass to actually absorb the contact noise and the transmission noise and so on and so on. So this, we did some initial research there and just did this summer a full-scale prototype to actually clarify the results. Also because we have these very large, very thin surfaces of concrete, my colleague Arno Schlüter is using very low temperature heating and cooling to activate them as large radiators. And then we evolved our structure a bit by going to a sandwich, because this will also be a nice piece where the glass disappears into just a small sliver. That is why we needed a sandwich shell, so that the glass would hit the insulation, and that we basically have beautiful architectural concrete with continuous geometry from the inside to the outside. So all of this is also totally overkill modeled. And on top we will have photovoltaics. Okay, so all of this sounds great, but the client then said like, yeah, okay, we know that we supported you for the last five years in this project, but we do need to see a full-scale prototype before we believe you, all right? So we just have this new building. The roof is by Gramatsu Kohler. This is the new building of our Institute of Technology in Architecture. The roof is robotically assembled. Super great place to work in. But what's special is our ground floor. We have this gigantic multi-robot fabrication laboratory. So it's called RFL, Robotic Fabrication Lab. This building was fresh delivered. We just moved in and I took my chance. I blocked 2/3 of the hall with a project that had nothing to do with robotics. So there we were. There we go for a full-scale prototype. Key point is, as I said, is not to have to build up anything from below. External pre-stress of the cable net, very lightweight, and then you can do the systems. We had to do everything the same as on site. So all these braces are needed because we're building on top of a building. So we're building all the way up there. So we mimicked everything the same. And more importantly, I took the gigantic, at the end it ended up being gigantic financial risk to do every single step with the industry partners that would do it. So that there is no more threshold, no more barrier to go on site. So these are the workers of Marti, extremely respected constructor in Switzerland. They did the only high-rise in Zurich, for example. All right, so there we go. This is typically where people start to frown a little bit, like, yeah, that looks a bit academic. Certainly when you see all these things. But all these elements actually nicely came together just in 1 week time by 3 people. And I want to contrast this very strongly again to the alternative would really be to achieve structural geometry would be months of carpentry, years of milling. That would be the alternative, right? And then building up all this scaffolding and so on. And so puzzling this little kit of parts together seemed okay. I always like to throw in that image, right? BIM, digital chain. This is what happens when you assemble it, of course. But then this money shot really clarifies why we are doing this. This is actually the cable net that carries all the concrete. The cable net weighs 500 kilograms, the fabric 300 kilograms, so that is 800 kilograms together. What is that? 1,800 pounds or something. Carries 40,000 pounds of wet concrete, right? So that is how lightweight this system is. And then also not unimportant is that this system can be easily reused, moved, shipped because it's so lightweight. So after this, we just cut it in 4 simple parts that will be reconnected quickly on site and lifted in place in just a couple of hours for the next shell. Nothing comes for free. Going from brute force stiff to flexible, somehow there needs to be a catch. And the catch is that the cable net needs to be pre-stressed such that it has a non-uniform pre-camber so that under the weight of the wet concrete, it hits exactly the geometry. That is important, of course, because we need to adhere to expected norm-defined construction tolerances, but also because we went, again, a little bit macho on this project, we needed to really hit that geometry because the shell is only 1.5 inches thick, right? So or thin for this large scale. These measuring devices is, by the way, this works very nicely theoretically, but will not work in real life because you generate all the pre-stress. This element is a millimeter longer. This beam moves a little bit. This edge was reassembled a little bit. So the cable net will not be at all what you need. If you then see all the links on the outside, you have about 100 links on the outside. That gives you 90 trillion combinations. So which one of these combinations will redirect the cable net such that you hit the geometry? And that is exciting. In our center of research is highly interdisciplinary, the NCCR Digital Fabrication. And there's people that actually do this as a research, to actually take such a highly indeterminate problem and to reduce the degrees of freedom to exactly tell you from the 90 trillion which ones you need to do to redirect your shell. And that worked beautifully, and we have all the data. So we basically gave this Formwork system a little bit of smartness, some algorithms, a little brain. This is the fabric being put on top. Another thing is that the design of the node was actually optimized such to be competitively cheap, to be made only with simple techniques, and also that gave us very simple ways to actually attach the reinforcements, for example. And we use this carbon fiber reinforcement, so textile reinforcement, because of the thinness of the shell. Corrosion would be an issue with traditional reinforcement, but also can you imagine pre-bending all these rebars? You would not even want to start, right? So that would make it ridiculous, while these carbon fiber mats can very easily be bent. And because we have this reference of the node every 40 centimeters, so every 1.5 feet, suddenly this crazy project becomes extremely straightforward. You have these space holders there, you can just quickly bend it, and so on and so on. So a lot of concrete chemistry in this was done by Lafarge-Holcim. We need a little bit more work on that. Amazing material, but a bit too sensitive for the real conditions that we had to deal with here. You cannot use typical shotcrete because you would blast through the fabric. So this is low pressure application, then vibrating. And so even after vibrating, the concrete doesn't flow off, so it nicely stays in place. And yeah, this was pretty intense. This gives you a sense of the scale a bit. And I just want to quickly pass here, because this is Tom van Mele, with whom I co-lead the group in green. He spent 24/7, half a year of his life to make this happen. And then Dave Pygram is the architect that did a lot of the development on the node detail as well. All right, the process, the concept, again, to clarify, is that it uses a cable net, false work, a fabric shuttering, and very simple system to attach the textile reinforcement, and then the very thin 1.5 inch layer of concrete could be then placed very simply. We worked with 40 different companies to really push this system to be as non-academic as possible, meaning as realistic as possible to be deployed immediately as a formwork system. And so we really pushed all components to be as cheap to be fabricated as possible. So the fabric here, you still see, I will come back to this, a lot of manual different steps to get there. And then the edge beams was actually quite a shortcut. There you can imagine that also the edge conditions could be much more standard and reusable and so on, and flexible, but in this case we were already risking so many different steps. We wanted this edge beam as a clear reference for our models because first and foremost we are benchmarking a truly different way of shaping concrete. So here we start with this because you see that it nicely was snowing. This project started in January, ended in August. That is ridiculously long, but because we did every single step along the way with partners from industry, they now fully understand why we went one step forwards, two steps backwards, one step forward, three steps backwards, and they have actually signed a report to the client that they will do the next one in just 8 weeks, which is what you would expect, well, minus the months of milling you would need to do for the formwork and so on. So some nice spider web action, and then we'll also see some analog form finding, this thing nicely coming together. This is just before pre-stressing. As I said, the node detail really allowed us to, in a very simple way, have all these placeholders and then assemble all these elements. The concrete, my mom was visiting. Yeah, that is something where we have to go back to the drawing board. Well, not us, our expert partners, because this was too laborious as a process. So we have a few ideas, and no one seems to be worried that it will not work 100% next time. We had a few kind of issues, a few patchy kind of situations. The concrete is not up to standard for the Swiss expectations, and so that is something that they, again, our expert partners don't seem to be worried about. So there you see the robotic fabrication lab with all the robots by Gramazio Kohler pushed in the corner, and us claiming the main views. It was actually harder to do it in the hall because you see it barely fits, and to be able to get everywhere with these people carriers, with these Manitous, was quite a challenge. With the photographer, you get a sense of the scale a bit, and even though the real structure will have the 2 layers, this is designed only for self-weight, the 2 layers will taper down to exactly the same thinness that you see here. So this will be the appearance of the shell at the end. And I'm just waiting until the end of the credits because we added a little Marvel style superhero encore to the end of this thing. So the point of the prototype was to test the system, to develop it together with our partners, but was not necessarily to move it on site, as some people asked, and so there it had to go. So this dinosaur came in to basically nicely eat it away. But after all of that, the client plus my university was quite convinced that we should absolutely push it, and so we got a commitment to go on site next spring. Seems easy, right? So not 100% perfect on the concrete, but nonetheless, exciting that we managed to do it at this scale. All of this is possible because we do everything computationally. So everything is basically, so our colleagues from Bollinger Grohmann, a big engineering office known for complex geometry, called our approach BIM on steroids. And that is with our open source computational framework that goes live this week at Acadia. And so it's going to be released, and this will change our world. But anyway, I don't have time to explain why, believe me. And, but basically everything that I've shown, both the armadillo and this one, everything will be shared open source and much, much more on how this was done. FE analysis will suddenly, Rhino will become FE, FE will become Rhino, fabrication, everything at the same time. So there it is. I particularly like, again, this link between how it was made, these traces of how we optimized it, the beautiful hanging of the fabric. When you zoom in, you get this very unique kind of texture. It looks like a comfy pillow, but it's actually cold and concrete. And this is indeed how we rendered it before that. But can we go one step further? We are already self-critical. Okay, extremely lightweight, but can we also include reinforcement? And that's why we do this 3D knitting that we are scaling up to full scale. What's cool about 3D knitting of textile? This is a non-orientable surface like a Möbius strip. This is knitted in one go. So pretty cool, but you can do many more complex things just in direct knitting. And then this is where it gets exciting. When you then work together with colleagues that do concrete magic, like my colleague Robert Flatt and his group, then you can use this high-strength cement paste to stiffen that. And then what do you end up having is a very complex, extremely controlled geometry that is super lightweight. And that can be just replaced as a lightweight formwork system. So I'm not yet suggesting that we should also use this as a reinforcement. That we will demonstrate in a couple of years. We will do all the necessary research. What we already have for free here is a lightweight scaffolding formwork piece where you can include traditional rebar. So there is absolutely no reason to not use this, and that is why we also demonstrate this on the small-scale bridge prototype. It's 7 feet long, so not that big. It uses these splines to be self-stiffened. And all of this yellow, which you see here, weighs only 400 grams, so that is less than a pound. And you see that another advantage of knitting is that you can include these channels and all these additional features that allow you to add, to not have to cut them, make cutting patterns, stitch them, another process, and so on and so on and so on. So there it is, stiffened. And then with this fast-setting, high-strength cement paste, then this shell becomes stiff enough to be able to cast or pour or spray regular concrete on top. And so we are now pushing this to make a 70-foot-long bridge by May. And I already am looking forward to the money shot, which will be 4 assistants carrying the entire bridge on site that will then serve to cast and pour the entire concrete without any support from below, using, again, some material magic, but more important, strength through geometry, right? All right, and for all of those of you that thought that I was wrapping up already several times, this is the real wrap-up. I want to quickly come back to the Biennale, because everyone looked at this piece, but this piece was only there to get your attention. This piece, okay, it showed that you can do exciting things bottom-up, rather than a sketch and then make it happen. It showed you that we discovered these forms with historic tools that we brought back and extended through computation, tools that until quite recently engineers discarded as appropriate to teach architect structures, but irrelevant for real engineers. Well, this is real engineering. We really discover exciting starting points. But the main message were these floors. Starting from the traditional tile vaulting, Guastavino vaulting. I'm jealous that you have so many beautiful examples here on site. How we translate this in an African context to really capitalize on local labor and local materials to provide perhaps a more appropriate way of construction. How we can translate this in our context to make extremely thin, so more than 70% of weight savings on floor systems. We all need floors. But structural geometry is very complex geometry and is extremely expensive to make, right? So you need a double-sided mold to cast your beautiful geometry and so on. And this immediately reduces its application to, for example, a repeated unit and so on. And that is why we showed the last floor to show the potential of the excitement of nowadays that our digital fabrication is scaling up really to construction scale. And that we, for example, in this case, we can directly 3D print the floor unit by itself. But this 3D printed material is as weak as the tiles that we used in Africa. So let me repeat or remind you, peanuts in compression. And if you take any little piece out of this floor, so this is about 1 inch in thickness, then it snaps like dark chocolate coming out of the fridge. Just to give you a sense a little bit on its bending capacity. And that is why we actually pre-crack the structure. By pre-cracking the structure, this is not only logistically a good idea, but this actually controls the force flow, because we tell the structure, there, I cracked you, so you cannot transfer any bending capacity. And that is exactly what, for example, Robert Maillard did in his beautiful bridges. He made a crack here, a hinge there, a hinge in the middle, a crack through his structure, and a hinge at the end. And that allowed him, even when the mountains would move, that he always knew exactly the equilibrium on the inside. No surprise that he used graphic statics to trace the geometry of his structure. And now through very advanced and new technologies in 3D printing, we can basically take also this precision to have more sophisticated interfaces. Also there, we actually demonstrate that this floor is up to code, up to expectation when it comes to structural capacity that it needs to take. And if you don't believe me, this is half of my team standing on something that has the material strength of chocolate. That is one of the things that we wanted to show. Our battle is that when I present a 2 centimeter unreinforced concrete or 3D printed floor, people make comments like, I would never want to come in your building. So you're crazy, you're dangerous, what are you doing? If you proportionally look at this shell, for the span that it has and only the 15 centimeters, this one is actually more extreme. And what I on purpose didn't tell you before is that this shell is not only self-supporting, it's also supporting most of the weight of the Vanderbilt Hall on top, which means that 2 to 3 million of New Yorkers are absolutely risking their life every single day when they're commuting in and out. This ignorance is not new. Beautiful tile vaults at the Met were destroyed due to ignorance. They should have looked at the load test of the Venus. Can you imagine the impact in high rises when you make the floor 70, or we can even go higher, lighter? And recent research by John Ochsendorf and his PhD student Catherine de Wolf have shown that for 10-story buildings and higher, even for ridiculous floor spans, 4-meter spans, 3/4 of the contribution to the self-weight of the construction goes to the floor, and this, for relevant floors, is almost the entire contribution. So why not focusing on this element? And if we then start to not layer all our features, in Singapore, a typical floor depth is 1.5 meters, which is, what is that, 5'6" or something? And that is because there is a separation of all these elements. If we can start to combine this, Arno Schlüter has built in a high-rise in Singapore, you can actually fit in 3 floors where 2 floors used to be by basically taking the synergies of the structural efficiency, taking the cavities to engage the media to activate heating and cooling and so on and so on. But at the end of the day, I get excited that structural geometry is beautiful geometry. And if you want to learn more about it, Ayla nicely mentioned already our old book. But yesterday, this came out. This is our book with detail, where we start from all the objects in the Biennale and we explain the precedents, the principles, and the potentials, and where we also tell all the behind-the-scenes story of how we built this stone shell, with a lot of perhaps too candid interviews with all parties. All right, that's it. Thank you very much for your attention.
We could open it up for questions.
Maybe.
is your guys' research with the false work.
Yeah.
And I understand the progression from the cables to the fabric concrete casting, but I'm wondering what that might mean going back to the armadillo structure, what that means for larger blocks.
Yeah.
I was just curious
Yeah.
if you guys have a research progression for that.
Yeah, we do, but it's a little bit premature. We don't have the large scale. Another one that we're planning is also May, and the reason why May is that we are being reviewed every single year in May, and so for May we are planning a few kind of ridiculous things, and so how we are addressing this is in two ways. That's why I showed the teaser with the box that became an arch, the CCTV that due to its discretization could stand and so on. We want to address this one way using that, but through smart discretization to use a masonry model to actually build in stable sections. And what's exciting there is that when you have a pure masonry model, then what you take as, for example, frictional interface, you take the typical Coulomb friction you would take for stone, for example. But if you actually start to explicitly control that and put limits on this friction, then this could be the starting point on a requirement for an interlocking feature. Like, for example, you could extend the range of stability or building in stable sections by not saying everything is perfectly smooth and needs to just balance by itself, but you could actually work with in-between kind of features that are designed just to overcome that stage and so on. So there's the two aspects. One is to generalize the masonry model and to show what you can do with that. And then second is to actually relate the abstract values of the masonry model to constraints on detailed design. And this is not only in stone, this can also be in timber, in whatever. But why we are also pushing this and why I think there is a lot of value to push it in this direction is that if you start from a masonry model and that constraint, though, that means that you anyways will have quite simple contacts and interfaces, meaning that you don't need to on-site need to start welding and attaching and so on to make it stable at that section. And so we are actively looking at it, but it's a much, much, much harder problem. But forgive me to having built that on a regular formwork, I think we were pushing things already a little bit enough. Yeah. But yeah, so yes and no, I don't have anything quite yet, but a lot of ideas. Yeah.
Thank you.
Thanks for the question.
Combination of high tech and low tech, and saying, you know, we really need to optimize more labor in certain conditions. Do you think, and then also kind of understanding the extreme tolerances that you're dealing with in other conditions, to what degree do you think that there's potential in kind of some of the surveying on site to move into a kind of low tech version of, say, the cable reinforcing?
Yeah, yeah. No, that's actually a great idea, and I don't want to answer to every question. Like in the next phase of the NCCR, we're doing exactly that. Is that indeed we are looking both at the high tech for precise, but then also low tech strategies, having even AR, simple AR kind of things with a cell phone tells you when your brick is exactly there where it needs to be and things like that. Because in Africa they all have cell phones, for example. Because it is really a challenge. It is. Oh, that was not a joke, right? Every single person in Africa has a cell phone. Ah, okay. All right. But what I wanted to, I lost my train of thought now a little bit with trying to be funny. Sorry. No, because now actually there is a lot of anxiety with respect to to what extent really is the kit of parts, the guide work, for example, will it really always guarantee that you somehow stick to that geometry? We add a lot of geometrical safety factors, so we add mass and more materials to make sure that if there is a deviation that you actually still hit the zone where you want to be, and so on. So we're doing these kind of measures. But of course, if we could start to translate smart ways to describe geometry in 3D, that would help a lot. And so one of our colleagues, Roland Sigwart, is interested in doing it through low-tech kind of devices. Yeah.
And is part of the release that's going to change our world, does that include the simulation of loading on the...
Yeah, sure. Okay, so what it is that it's an open source platform, Python-based, pure Python, which means that it is entirely platform and software independent. It actually gives you all the glues. So we realized in my group, but anywhere, that everyone is constantly reinventing the wheel by setting up their own data structures, their own grasshopper spaghetti models and so on that you can never share with anyone in a meaningful way. So no one is building upon each other's knowledge. So we develop extremely robust data structures. We give a core library that if you extend this library, anything that is built upon this library is compatible with anything else built upon this library. And so that is exciting because we enforce this. So everyone in the NCCR, there's a full commitment. The new director says so in the second phase. I'm the new director of the NCCR, to basically use this as a computational glue. And that means that we actually are really proactively working on developing also research output that is fully and 100% transparently reproducible and shared in an open source manner. And so what we also do is not only the data structures, but we also make all these connections to all your favorite softwares. So how many months have people wasted their time, every single one again, to have a connection to an FE software? By pure frustration, everyone uses Caramba in Grasshopper because it's more readily available. But we actually give you, just by changing one line of code, your Rhino interface becomes a full-fledged, sophistic, ANSYS, Abacus kind of interface. And so we did that for you in the background. This is 5 years in the making. How many researchers are working in MATLAB and would like to not have to share like clumsy text files back and forth? Again, one line and you will be able to link all these things together. So we did a lot of infrastructure in the back. And to show that we really mean it, with the first release, there will be an AGS package, that is Algebraic Graph Statics, which is our backend to a graphic statics software. Then we will release TNA, which is basically Rhino Vault for professionals, like entirely customizable. And we will release the FE package, which is the one that everyone seems to be kind of waiting for. Because what is important in the back is that certainly as a lesser informed user, the meshing is extremely sensitive. And so to generate proper FE meshes based directly on Rhino geometry is kind of also not that obvious. And my postdocs in structural mechanics did that for the users and so on and so on. And then the last thing is we really did a big effort to make it entirely platform and software independent. So that means that anything you develop as an extension to the framework will run in Blender, in Rhino, in Maya, will be compatible with Arduino, with Dynamo, with Grasshopper, and so on and so on. That's what we did. Sounds too good to be true, right? Oh, sorry.
For building officials who, thank you. For building officials who depend upon getting reams of structural calculations based upon stress systems with the design drawings, how do you convince them that this will work?
No. This question comes back all the time. That is also what we fight every single time in any project we do. So in Switzerland, we're lucky that actually you can demonstrate all of that. You actually don't even need an engineer. It's all onto whoever wants to take responsibility. So that's a little bit unfair. So I'm in a good playground to actually provoke or show and so on. But we made this split 150 plus years ago. No, that is much longer. So in 1820, right? It went in two ways, and we forgot entirely one way of doing things, right? So now the last 10 years, we brought this back. So we have a huge kind of legacy and habit to catch up on. But I see my role a little bit more to demonstrate that there is another route, that we might want to actually bring these things back. And also to clarify that these methods are not soft versions for architects and so on, but we need a bit of work and we need convincing demonstrators, we need real projects, we need to do a lot of testing, and I'm fully aware of that. So we need to do all of that to actually also then develop the appropriate norms and codes and whatever that we can really fall back onto, which we don't have. I mean, if you look in the Eurocode, there is one page on an arch, like one page in the entire, I mean, that is ridiculous, right? So we need to do the background research on that, but we also need to work on the education. And so I see myself, our group, our projects, more to clarify what the potential is, because I'm fully aware that we're not there yet and not anywhere close. But yeah, we are pushing as hard as we can and try to share our message and also our interest in understanding these methods, and even, for example, more humbly, starting with a better starting point or a more interesting starting point. I mean, you can still do all the regular engineering. You will notice that actually if you, for example, use Rhinovolt or something like that, and you paid attention and you have all this good double curvature in there, and then you give it to an engineer, and then they will be like, huh, this actually behaves extremely well, so we don't have to do anything to that, right? And then so by also adapting different ways of designing, you could also push things a little bit further. So yes, there is a lot of work, but no, so it's not an answer, but it's a reality, and we are trying to address this. But I think it's important, though, because something that I didn't talk about, because I didn't show our recent, we built something because mycelium is so popular, building things out of mushroom, but it's even more weak. And so we built a fairly large structure out of mycelium only to make a point, again, that's strength through geometry rather than through material capacity. And there also people are a little bit confused by it. What I wanted to say is actually that suddenly, if you see the 3D printed floor, which really happily carried more than a ton of ETH nerds, right? So this is already a good starting point. That this floor is because of a good geometry, and we are really starting to have these digital fabrication techniques that can go to that scale. And so that means that, in fact, if you talk to material scientists, there is a lot of exciting materials, 100% waste, CO2 absorbing, and so on, that were discovered a decade, 2 decades ago, that were discarded because they had only 20 megapascals, or only double the strength of a typical concrete, and so on. And they were discarded because people were always focusing on beams and on elements where you needed a totally different level of strength capacity to feel safe about the material. So I think that is also important, that actually if you get the geometry right, and more importantly, if you now find competitive ways to make that efficient geometry, that you can start to introduce materials that will help us not be dead in 6 to 7 generations from now. Because I didn't talk about this at all, but we have only one planet. At a certain point, we will have to do things better. And it will be the structural designers and engineers that will be the heroes. That's a bit cheeky.
So you talked about the cable net framework and the problem of trying to pre-tension it so that when they put the concrete on, it would settle into place.
Yep.
How much does it move when you put the concrete on it, and what were like your biggest errors in terms of where you wanted it to be?
So it entirely depends on the proportion between the pre-stress and the self-weight. So it actually doesn't move that much, but it moves enough that you need to control it. So we started with 4 centimeters of deflection, and we got it to 1 centimeter. So that is the control that we got there. And so for concrete, and I find this a weird measure, but for concrete construction, it's actually independent of the scale. It's 1 to 2 centimeters is the required construction tolerance in Europe. Yeah, so that was nice. Yeah, that was a good result.
On that note, maybe we can continue the discussion at the reception, but thank you.
Thank you. Yeah. Thank you.